In this video, I will write the proofs of some simple statements with quantifiers for all and there exist. The statements I've chosen are very simple. They are things that normally we would not bother writing a proof for. Nevertheless, I want to use them so that we can fully understand the building blocks of a more complex proof, and later we can put them together and write those more complex proofs. Here's my first theorem. I'm going to call A the set with elements 2, 3, and 4, and I claim that for every x in A, x is positive. Okay, as I said earlier, this is obviously true. This is not something we would normally bother to write a proof of. But I want to nevertheless write a proof in something as basic as this, so we can observe the structure of the proof and then use it later in a more complex proof that has for all. So how would I prove this if I insisted I need a proof? Well, I need to verify x is greater than 0 for all the elements in A. And there are 3 elements in A, so I need to check them all one by one. Well, I need to check that 2 is greater than 0, check. 3 is greater than 0, check. 4 is greater than 0, check. I think that's it. This field square means end of the proof. Okay, let's look at another statement. This says something similar, but for a different set. Instead of for A, for the integers. For every integer x, x is positive. And well, can I prove this? No, I can't, because this is false. Not every integer is positive. Okay, so instead of showing it is true, I'm going to show it is false. What do I need to do to show it is false? I need to prove that the opposite of the original statement is true. What's the opposite of saying that for every integer x, x is positive? What does it mean to negate that? Well, to say that it's false that every integer is positive is the same as saying that there exists at least one that isn't. So there exists at least one integer x such that x is less than or equal than 0. Okay. And I want to give a name to the relation between these two statements. We're going to say that the second statement is the negation of the first. And what that means is that it is the opposite. The negation of a statement is something that will be true exactly when the original statement is false. Now, in this case, this was quite simple. We didn't need to be so formal, but in other cases, it's maybe more complicated. And in general, to prove a statement is false, we can simply prove that its negation is true. How do I prove this? Now, this is not a statement with for all. This is a statement with there exist. How do I show that there exists an integer with a property? I only need one. Well, an easy way to do that is by saying what that integer is. I only need to take one, I get to choose it as long as it satisfies that. So I'm going to say just take x to be minus 6, for example. And now what I need to verify is that minus 6 is an integer, yes, and that minus 6 is less than or equal to 0, true. And that completes the proof. Okay, so next let's look at another theorem where the proof is going to take more than one line. I want to prove this theorem that says that for every integer x, there exists an integer y such that x is less than y. And I've already talked in a previous video about why this is true, but now I want to write a proof. Let's see. The theorem begins with for all integer x. There are infinitely many integers, so unfortunately in this case, I'm not going to be able to check them all one by one. I would never finish. So I'm going to need to try to prove it for all values of x at once. The standard way we begin proofs like this is by writing let x be an integer. But the important thing is not what we write, but really what it means. The convention is that when I write this in a proof, this means that I am fixing an arbitrary value of x. And there are two important words here, fix and arbitrary. Arbitrary because this must work for all integers. I don't get to choose x. X should be any here. Otherwise my proof doesn't work. I want it to work for all integers. And fix, I'll come back to that, why that is important. So once we have fix x, now I need to prove that there exists a y with a certain property. And we already saw in the previous example that to prove there is a y with a property, the easiest way is to say what y is, to just choose y. So I'm going to say I'm going to take y to be something, and then I'll verify it has the property. So after that, what I'll need to do is verify that this y I've chosen is an integer and verify that is greater than x. What do I choose as y? Well, what is greater than 8? For example, 9. What is greater than 20? For example, 21. So the easy way is if I fix x and I ask you for a greater integer, just take x plus 1. It's not the only choice, but it's one that works. And then if x is an integer, y is also an integer. And whatever x is, x plus 1 is greater than x. And that's it. That would complete the proof. Don't get intimidated by the formality of the proof. All I've done here is say that if I fix x, I can always take y to be x plus 1, and that will be an integer that is greater. That's all. And that agrees with our intuition of why this is true. But I want to come back here to this word fix. Why was it so important that I fix the value of x at the beginning of the proof? In the second line, when I say that I am taking or choosing y to be x plus 1, x must mean something specific. If I don't fix x at the beginning, it doesn't make sense to choose y to be x plus 1 because x doesn't carry any meaning. In the statement of the theorem, x is a quantified variable, so x doesn't have an intrinsic meaning. In the process of the proof, before we operate with a variable, we must have fixed its value. You may think I'm being nitpicky here, but if we are not careful with this, and if we don't pay attention to doing it this way, when we come up with more complex claims, it's easy to write bad proofs, or even to write pseudo-proofs or false claims, which is worse. So, the structure is very important. I must first fix x, arbitrary, then I choose what y is in terms of x, and then I verify the extra conditions. We can take this as a template of how to write a simple proof with two quantifiers, and we will use the same idea with much more complex such claims when we try to write proofs of theorems involving the definition of limit.